Hey everybody, we have a what I would call a counterintuitive problem here in terms of the size of the answer. Now let's work with a concrete example here to make sure I'm being clear about what I'm looking for. This is called the omega function. It counts the number of distinct primes. Now right here, if you rewrite this based on prime factorization, 72, shall we call it a large number, but it only has two prime factors because you can write it as 3 squared times 2 cubed, right? And you'll recognize that as 9 times 8 is 72, right? So the answer here is just 2. And again, it's not because there's 2 right here, it's just that there's 2 distinct prime factors. So that's what omega does for you. Now right here, we want to do the omega of this number right here, this large number. This is easy to manage, very tractable. Right here, how many distinct prime divisors would you have? Divisors or factors, that's synonymous right here, folks. Now this is fine, and obviously it's not doable manually like we did right here. So let's get down to the approach here that'll lead to what I call a counterintuitive result. Just based on the properties of factorial, you can factor out a 14 factorial and you're left with a 1, because you can think of this as 1 times 14 factorial, right? Now the definition of factorial makes the rest of this clear. 14 factorial times 15 is 14 factorial times 15, which is 15 factorial. And similarly right here, 14 factorial times 15 times 16 is 16 factorial, okay? So what we get right here, and here's where this counterintuitive part, what I was surprised at the answer. It was relatively small, okay, but it's kind of a fluke, I think, because if you do the arithmetic right here, the factorization leads to some simple arithmetic. If you sum up all these numbers, you get 256. Yeah, and you can see what I mean now. 256 is just 2 to the 8th, okay? 256 is 2 raised to the 8th power. So just a single prime factor in this quote large number. Now right over here on 14, certainly 2 is one prime divisor of 14 factorial. 3 would be the next prime divisor of 14 factorial. Skip 4, right? 5. Skip 6 because 2 and 3 is already taken care of. 7, right? And then we bump up to 11. And finally 13. And there is no need to count 2 twice here. So we have 1, 2, 3, 4, 5, 6. So we have 6 distinct prime factors. You could think of, if you want to call this n right here, n is equal to this sum, then we have omega of n, number theoretic function that counts the number of distinct prime factors. It has a nice summation definition. You can just do sum ones of all the p's that divide in. Okay, now, so this is equal to 6, and that's the answer to the question. Okay, fun problem, folks. And again, I never would have thought that this meager number 6. Now, again, you can have large numbers with very few prime factors. That we constructed one that was 72, right? But still, these are super large. None of these numbers you could even compute by hand really very easily without making a mistake. Okay, then to boot, you sum them up, and it turns out there's only 6, okay? So that is our answer, and again, I like the approach. I like the fact that algebra bailed us out, and this monster numbers you can't even pronounce. We know this particular number has exactly 6 distinct prime factors, okay? So answer to the question up here is 6. Thanks for viewing.